Hey everybody, this is Dr. Venditti, and I'm going to be teaching you about the heat exchanger lab in PSE 475. For this lab, we have what's called an indirect heat exchanger, and we have two flows. Our first flow is house water that comes through here, and it goes down through here and out this port right here. That's actually on the tube side, so there's multiple tubes inside here. On the shell side, we have hot water. The hot water comes from our hot water reservoir. And then the hot water actually goes into this peristaltic pump, and then that pump pumps it on the shell side of this heat exchanger. And then the hot water comes out. So we have hot water on the shell side and cold water on the tube side. The house cold water goes in the tubes and then out, and it's disposed of. The hot water actually recirculates into this reservoir, and we maintain around a 55 to 60 degrees Celsius hot water bath. Okay. The other thing you'll notice is that for our cold water in, we have a thermocouple. Cold water out, we have a thermocouple. And then we have a valve here. So this is a needle valve that we can adjust the flow of cold water. On the hot water side, of course, we have our peristaltic pump that's pumping our hot water, and we measure the hot water temperature in and the hot water temperature out. The other thing I should mention is that we keep the inlet pressure of the cold water constant. And so for this geometry right here and that pressure being constant, we get a constant flow of cold water. Now what I want to do is I want to show you the control interface for this. First thing I'll mention to you is we have the cold water out temperature, cold water in temperature. Then we have the hot water out temperature and the hot water in. And so as you can see, cold is coming in now around 29. It's being heated up to about 39. The hot water is coming in around 65 degrees Celsius, and it's coming out at 49 degrees Celsius. So we get heat exchange between the hot and the cold. The other thing that you can see here is our pump control. So right now our system is in manual. That means that we're actually setting the pump speed. So at manual, we're right here at around 25% pump speed. And over here you can see that we got a reading of 2.6, about 26%. So if we want to increase the pump speed, we can just move this dial, and I'll move it up to 50%. And that would be a bump change in my manipulated variable, which is the pump speed or the hot water coming into the heat exchanger. And then I can do a bump test where I go down. So I'll go back down to 25. Okay? So this is manual control, and that's open loop. So what we can do from here is we can get the system in steady state and then make a bump change in the pump speed. And then what we'll do is we will watch the cold water out temperature as a function of time. That's called an open loop bump test. And typically we will collect all the data, and then we will fit that to a first order plus dead time system, if it is actually a first order plus dead time system. The other things I want to show you on the window are the red, yellow, and green curves. The red is the cold water out temperature. That's our control variable. That's what we're trying to control. Yellow is the set point. So when we have the system in automatic, that's the set point where we want our cold water out. We'll use that later. And then the green is the pump output. So that's right here. Okay. Okay, now the first experiment that we're going to do with this system is an open loop bump test. Now an open loop bump test is where we're in manual control. So you can see right here we're on the manual control. So that means we can control the pump speed. What we will do is we'll make a step change in the pump, and we will monitor the cold water out temperature. That's our control variable. Okay. So in this case, we're going to start off at 26.3, is our initial pump speed, and I'm going to make a plus 10% bump change in the pump speed control. So 26.3, I'm going to go to 36.3. Okay. Now when I hit enter, our experiment will start. So enter. So this is time equals 0 at this point, and you can see at time equals 0 we had a bump change, step change in our pump speed. And now what we'll be doing is we'll be looking at the temperature of the cold water out. And you can see here, that's the red line. You see it's flat for a little bit of time, and then it starts to go up. What you can think about now is the dead time. That's the time that it takes before any change is seen, and then you can see the response to the change in pump speed. So what we would be doing at this point is we would be taking time and cold water out temperatures, and then we're going to take this curve and we will fit it to a first order plus dead time system. If you notice, nothing happens for a little while, and then we get this exponential decay, and we hope that we go to a new steady state. That would be indicative of a first order plus dead time. And what we can see now is it's somewhat difficult to see, but we went from one steady state value, and now we're leveling off at a second one. Okay? Now we have collected all this data in a spreadsheet for you. And not only that, but we've done multiple step experiments, open loop bump experiments. And your job is to fit all of those curves to a first order plus dead time system. Okay, now what we're going to do is we will demonstrate a closed loop servo test. That is where our system is in automatic control and we make a change in the set point. We have tuning parameters that we're evaluating, and we see if those tuning parameters drive our controlled variable, the cold out temperature, to our new set point. So let me just show you how we do that. First thing we do is we make sure that our system is in manual, and then we adjust our set point. So our actual cold out temperature is about 35 here, and I'm going to make our new set point be 40. And then I can hit return. Now the set point's not being used right now because we're in manual control. The second thing I'll do is I will set my Kc and my tau I value. For this experiment, I'd like to try a Kc equals 10 and a tau I equals no integral action. So I'll just put a 0 in there, and the computer will know that means that there's no integral action. So we now have our Kc and our tau I set. At this point, we're going to hit the manual to automatic button, and that will start our experiment. What we will be doing is we will be watching this red line, the cold out temperature, and hopefully it will gradually go to the new set point and then remain there. So let's just start the experiment. So I'm going to go manual to automatic. So that's time equals 0, and what you can hear is that the pump started to speed up. Here's my pump speed. It sped up, and because it noticed that the control variable was much lower than the set point, and so the pump speed sped up, and then it's kind of gradually lowering it because our control variable is actually going towards our set point. Now let's see where this system ends up. It looks like the system is going to end up with some type of offset, and that's very common because if you don't have interval action, you can have some offset or steady state error. It looks like we're getting a little bit of oscillation here, but not too much, and it looks like we're now steadying out at this value. So like I said, we're actually taking the data for you, and you'll be supplied the data of those things. You'll get the set point as a function of time, the control variable as a function of time, and then the controller output as a function of time, amongst other things. And from that, you can calculate how this tuning parameter set works for this experiment.
here I am going through a self-tuning experiment. First, I had the set point put at 5 degrees higher than the inlet temperature. The outlet cold valve position is on 5, the feed pressure is at 20, and then I use PI control with a KC value of 8 and a tau I of 0.1. So I let the system equilibrate here, and then after it reached that equilibrium point, I went through the automatic PI tuning. So as you can see on the screen, basically what we just did previously, finding these values manually, the computer is now doing it itself. So the computer will find the ideal KC and tau I values for a fast tuning, normal tuning, and slow tuning. And obviously a fast tuning is going to have more aggressive values, while slow tuning will have less aggressive values. You'll be able to see that in the numbers that are given. Alright, for our last activity, we are going to be performing regulatory experiments on the 3 tuning sets that we found previously doing automatic tuning. Now, just as a reminder, a regulatory experiment is when we keep the set point constant and we add a disturbance to see how the system will react. Now, again, we are going to be doing this for each of the tuning sets that we found previously, including slow, normal, and fast. Before we perform these experiments, first we are going to put the set point at 5 degrees above that cold water temperature. We're going to put the system into automatic control and input that KC and tau I value for whatever tuning set we are going to be testing. We need to let this tuning set reach its steady state, and then once it reaches that steady state, we are going to mimic a disturbance by turning that cold water valve from the 5 to the 50 position, and then we'll see how the system reacts. We'll collect data until it reaches that steady state point again, and then we are going to repeat these steps for, again, the slow, the normal, and the fast tuning sets.